So the next operator is the NAND operator, and this is the graphical notation for it. And you can note that it looks similar to the AND operator, but it has got a small dot out here, small round circle out here. So this is the same as the NOT, if you can recall. This is the NOT. So that's why it is called NAND, because it represents NOT of AND. So it is NOT of AND. That is why the algebraic expression for this can be written as x is equal to AB, which is AND, A dot B or A dot AB, and then NOT of this. So complement dash. And what is the truth table? The truth table is like this. I have A, B, and X. This is my 0, 0, 0, 1, 1, 0, and 1, 1. So this operation is NOT an AND. So AND will give me a 1 for this and 0 for all of these. So if I just do an inversion of this, invert of the AND, then I will get a 1 for the first three and I will get a 0 for the last one. So NAND works like this, 1 and 0. So this is the NAND. So similar to this, we also have the NOR, which is NOT and OR. NOR. Again, its symbol is like this. This is the OR, NOT of this, so NOR. So I have A, B, and X. So the algebraic expression is A or B, not of that. So NOR. And what is the truth table again? Truth table, I have A, B, and X. So 0, 0, 0, 1, 1, 0, 1, 1. So here the ones that we got for OR were here, here, and here. And it was a 0 for this. So it is not of that. So I'll get a 1 here. And I will get a 0 for all the rest. So this is your NOR operator. And then another one, another very important operator is your exclusive OR or XOR. Exclusive OR, which is also in short we call it as XOR. Exclusive OR is something like this. The symbol is like this. Then there is a gap, and then there is the OR symbol. Okay, so A, B, and this is X. This is connected. Okay, so this is your exclusive OR. How does it work? Well, the algebraic expression is written like this. A, this is a special symbol for this, A exclusive OR B. This is the exclusive OR symbol that you can see here, plus which inside a circle. And this can be written as A dash B, that means A complement of B, or A B complement. A complement B or A B complement. So remember, this is AND, this is AND, okay? AND of A complement and B, or AND of A B complement. So its truth table is like this. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. And here the output is a 1 only if the two symbols are different. The two inputs are different. So here you see, in this case, in the first case, the two inputs are same. In the last case, the two inputs are same. But in these two cases, the inputs are different. So if the inputs are different, the output here would be 1. For others, it would be 0. So this is how your exclusive OR works. And finally, the last one is exclusive NOR. exclusive NOR. Okay, and this is also known as equivalence. Equivalence, and it is written like an exclusive OR, the same symbol, but because it is a NOR, so there is a NOT out here. Okay, so this is an exclusive NOR operation, the graphical symbol for it. And the expression, algebraic expression, is this: exclusive OR AB, not of this. Alright, so not of this, not of the exclusive OR. So our truth table will be something like this: AB X 0 0 0 1 1 0 1 1. So what would be our exclusive OR? Exclusive OR had, I'll just write it using a different color. So if it was exclusive OR, I would have got 0 here, 1 here, 1 here, here. So now it's a NOT of that. So my output would be 1 here, 0 here, 0 here, 1 here. So you can say that exclusive NOR gives an output of 1 if the two input symbols are same. Output 1 if both input symbols are same. Okay, so this is your exclusive NOR. Now these are like the ABC of logical circuits. So to design logical circuits which perform some task, things like addition, subtraction, things like memory, constructing memory, for all of these you need to have some logical circuits, and these logic circuits are constructed using these logic gates. And as a result, as you can see, some input is given and some output you get from this logic gates. So when you combine these together, you get more complex circuits which is capable of performing more complex operations. Now before I wind up, one small gate which is there, which it's it is not used, it is used, but it is not so common, because you may find that it does not perform much of a thing. So here you see, this is known as, this is the input, this is the output. Okay, this is known as a buffer. This is known as a buffer. We'll see later on what happens in when we have to use a buffer. So here, whatever input you give, it takes one input. Whatever input you give, the output will be the same. So if you give 0, you get 0. If you give 1, you get 1. So this is the buffer gate. Now you can see here that the buffer does not produce does not perform any function. It simply takes the input and passes it on. So what is the use of this? The main use of this is for power amplification. Power amplification. So when you have a buffer that uses, say for binary 1, it uses 3 volts, and it will, if you give input 3 volts, you will get an output of 3 volts. Okay. However, the amount of electrical power that you need at the input will be much less than that of at the output. So if you give a power which is less than 3 volts as input, what you get as output would be a signal of 3 volts. So the input will require less than 3 volts to represent 1, whereas when you get the output of 1, you get a 3 volt signal. So the power becomes amplified. So the main reason why we use this buffer gate is to help other gates which require large amount of power. So if you have a gate which requires more power, then you can add a buffer in the before it, which will amplify the signal A, the signal strength A to X. So it will increase the power. So that is about the buffer gate. So these are the different logical gates which will make up the logical circuits. In our next video, we will look into the Boolean algebra and we will see how Boolean expressions can be constructed to create more complex circuits using these logical gates.